Chapter 4, Section 4, Irrational Numbers, Master Level. Right now we're going to look at something called a mixed radical. Well, you know what a radical is, and well, that's this. It's when you have a number underneath some kind of a root. So it could be a square root or a cube root or something like that. And what I mean by mixed, well, I'm not going to describe that just yet because I think that'll become more apparent as we go along. First of all, I just want to look at the square root of 81. And we're going to use prime factors, at least to illustrate my point. If you were to take the number 81 and break it down using a prime factorization tree, you'd end up with the following. 3 times 3 times 3 times 3. Okay? Well, that happens to be 9 times 9. Okay. Now we already know 81 is a perfect square, but notice if I have the square root of a number times itself, that's just the same as the number. Okay, in this case, 9. So I'm using the following property. Okay. If I have the square root of, let's say, m times m. Okay. Well, that's just m. The assumption is, of course, that m is positive. All right, well, let's look now at the square root of 75. Now, I would hope you'd recognize right away that we're going to run into trouble because 75 is not a perfect square. Okay? Therefore, this radical, it's irrational. Meaning that if you tried to work it out on a calculator, you would get a very long decimal. In fact, the decimal, it goes on forever and it doesn't repeat. The square root of 81, which is 9, this is not irrational. This is rational. Basically, a rational number is any number that could be written as some kind of a fraction, and 9 could be understood as 9 over 1. All right, so the square root of 75. Well, if I break 75 down into all of its prime factors, using our prime factorization tree, we would get the following. We would get 5 times 5 times 3. Okay? All of these are prime. 5 times 5 is 25, times 3 is 75. Okay? Notice how the inside looks a little different than this one. All right. We have 2 factors of 5, but only 1 factor of 3. Okay? If you look over here on the left, for every 2 factors that I had that were repeated, basically that just comes outside this radical symbol. So here's what it looks like. If I have 2 factors of 5, 1 factor of 5 can jump out, and that 3 is still stuck. Okay? The only way I could pull out a 3 is if I had 2 of them, but because I only have 1 of them, it stays as part of the radical. I have 2 factors of 5, so it's like they jumped out and just became 1 factor of 5. This is what we call a mixed radical. Okay? Because it is just that. It is a mix. This here is a radical, but this number here, 5, is not. Okay. Now, what's the purpose of doing all of this? Okay. Well, you guys have been reducing fractions for many, many years, and the purpose of reducing a fraction is to get the numbers as small as possible. That's sort of like what we're doing here. Okay. We're taking the number that's inside this radical, the number itself is called the radicand, and we're just trying to make it as small as possible. Okay, so it's sort of like reducing a fraction, but we're reducing a radical. So the number that is trapped inside here, 3, that's as small as we can go, and we were able to remove, well, what we didn't need. Let's try another example. The square root of 60. Okay. All right, so this time I'll show the prime factorization tree. Okay, just breaking everything down. This is 6 times 10. 6 is 2 times 3. And 10 is 2 times 5. Okay, these are all prime. Okay, so I can't go any further. So I'm going to group them. This is 2 times 2 times 3 times 5. Okay. So if we want to effectively reduce this radical, so it looks kind of like this one, we want to look for all of the factors that are repeated. Okay, well, I have 2 factors of 2, so that's good. Unfortunately, I have 1 factor of 3, just like this one, and I have only 1 factor of 5. Okay? There's nothing I can do with this 3 and 5, so they are trapped underneath this root sign. But I have 2 factors of 2, so I can pull them out, and it just becomes 1 factor of 2 times, I just don't need to write the times the root 3 times 5. Now because I can't do anything with these, I'll combine them again. Okay, so 3 times 5 is 15. So I read this, meaning I pronounce it as 2 root 15. But it is understood as 2 times the square root of 15. Okay, so this radical, the radicand being 60, I've reduced it as much as possible. This is as small as I can go. Let's do another one. The square root of 72. Okay, well, 72, just like 60 and 75, none of those are perfect squares. So the best I can hope for is that I can reduce them. And sometimes you can't. Nevertheless, let's see what we can do. So I'll do another prime factorization tree. Why not? They're kind of fun. Okay, 72. Okay, I know I can break that down into 8 times 9. This is 4 times 2. This is 2 times 2. And 9 is 3 times 3. Okay, so these are my primes. Okay, so that's the best I can do. So I have 3 factors of 2 and 2 factors of 3. Okay. So I need ones that are repeated. Okay, so I can pair those together and I can pair these together. So there's just 1 factor of 2 that, well, he's stuck. So these 2 come outside here, and these 2 factors of 3 come out as well. That's 2 times 3. And then I still have this root, and the 2 is still trapped. So my final answer is 6 root 2, or 6 times the square root of 2. Okay. So these 3 are what we call mixed radicals. So the remaining radical, the number inside, is as small as possible. Okay. So just to summarize, when we're breaking these down, every group of 2 equal factors inside the radical, so for example, I have 2 equal factors of 2, I have 2 equal factors of 3. Every time I see that, that is equivalent to 1 factor outside the radical. Okay? So if I have 2 factors of 2 inside the radical, it becomes 1 factor of 2 outside. Just like this, I had 2 factors of 2, 2 factors of 3, so it just became 1 factor of 2 and 1 factor of 3 outside the radical. So that's just to summarize what I've been doing. Moving on, mixed radicals, but instead we're looking at cube roots. But we're going to use the same method. So the cube root of 64. Well, hopefully you know that, well, 64 is actually a perfect cube already. So the answer is already 4. So it's not an irrational number. But I'm just going to demonstrate the process anyway. Okay. If I was to break down 64 into all of its prime factors, you would get the following. You get 2 times 2 times 2 times 2 times 2 times 2. Okay, so 64 is in fact 2 to the power of 6. All right. Now, when we were working with square roots, we were just trying to find groups of 2. But if we're looking for a cube root, well, we want groups of 3. Okay. Well, I have 3 factors of 2 here, and I have 3 factors of 2 here. Well, what do you know? Okay, all of the prime factors underneath this radical symbol are accounted for. And we would expect that because we know that 64 is a perfect cube. So I shouldn't have any left. Right? So for every group of 3, it becomes 1 factor outside. So this becomes 2. And then this group of 3 becomes 2. So what happens to the radical? Well, you can always imagine there being an invisible 1. We don't bother writing it usually, but I'll put it just this time. Okay, but the cube root of 1 is just 1, so I don't need this at all. And I get 2 times 2, which is 4. Okay? And we would expect that. The cube root of 64 is 4. Okay? But let's apply that now to a few examples whereby just by looking at it we can tell that these numbers here, okay, are not perfect cubes. So let's see what happens. Okay? So if I were to complete a prime factorization tree and write out all the prime factors, I would get this. 2 times 3 times 3 times 3. Okay? Because 3 times 3 times 3, that's 27. 27 times 2 is 54. So all these numbers multiplied together is 54. But I'm trying to find a cube root, so I just hopefully want to try and find groups that have 3 of the same. And we do. Okay. So 3 factors of 3 becomes 1 factor of 3 outside. Unfortunately, this factor of 2, well, nothing we can do. So it's trapped. Okay, and there we go. This is a mixed radical. Okay, the cube root of 2, and the 2 being what we call the radicand is as small as possible. Right? So we've effectively reduced this radical as best we can. Cube root of 48. Okay, well I know 48 is not a perfect cube, so I'm going to have some numbers trapped, we would expect. Let's do a prime factorization tree, why not? So this is 48. Okay. Well, I know 48 is 6 times 8. That's one way to break it down. And 6 is 2 times 3. Those are prime, so that's done. 8 I can break down to 4 times 2, but I'm actually just going to break down 8 like this because I know that 8 is a perfect cube. I'm just going to circle my prime factors, and there we are. So writing them out, I have, oh my, 4 factors of 2 and 1 factor of 3. All right, so we want to look for groups of 3. Well, there's one there, and, well, that's the best I can do. So those 2's jump out. There it is there. And then I have to write whatever's left. Don't forget this little 3. Okay, this is still cube root. And this is 2 times 3, the prime factors that are left over. And because they are stuck, well, I might as well combine them again. Okay, so the cube root of 48 can be expressed as 2 times the cube root of 6. Okay, so the radicand of 48 has been reduced to 6. That's as small as we can go. The cube root of 1080. Okay, so, ooh, speaking of which, there's a little mistake here. Right there. Okay, I said don't forget my little indices here, the 3. Well, can't forget that. Okay, so cube root of, alright, might run out of room here. See what I can do. I know that's 2 times 2 times 2 times 3 times 3 times 3 times 5. Ooh, that's a tight fit. Okay, that is 1080. So this is again a cube root, so I just want groupings of 3. So there's one, and there's another. And that 5, he's stuck. So this becomes 2 times 3 times the cube root of 5. So this is 6 times the cube root of 5. Okay, so that reduces quite nicely. We had quite a large number here, and now it's quite small. It's, well, 5. So just to summarize, just like I did with the square roots, for cube roots, every group of 3 equal factors inside the radical is equivalent to 1 factor outside the radical. Converting to entire radicals. Well, first of all, what in the world is an entire radical? Well, this is an entire radical right here, cube root of 64. Cube root of 54. Okay? When you see a number and everything you see is underneath the root, okay, that's what we call an entire radical, because it's entirely a radical. When you break it down and you have part radical and then part rational number, we call it mixed. Well, because it's a mixture of the two. So here, 3 root 10, or 3 times the square root of 10, this is a mixed radical. And all we're asked to do is, well, effectively go backwards and express everything here as an entire radical. This is actually pretty simple. In fact, I would argue this is a lot easier than what we've been doing. Okay. To create a mixed radical, we break down the number inside and we look for all the groupings possible and we pull out whatever we can. Well, all we're going to do now is the reverse. We're just going to take everything that's outside and stuff it back in. And the nice thing is, I don't need any prime factors. Okay, so remember, this is a square root, so every 1 factor outside, okay, is equivalent to 2 factors inside. So it's like I'm putting the 3 back in. So as soon as it goes back in, I have to write it twice, and that 10 is still there. All right? So everything's stuffed back in its place. Right? So 3 times 3 is 9, times 10 is 90. And there we go. This is an entire radical, mixed. Next, we have 5 times the cube root of 4. All right? So this is a cube root. So for every factor of 5 that's on the outside becomes 3 factors of 5 on the inside. So this is cube root. So this becomes 5 times 5 times 5 times the 4 that's still in there. Okay, so we just worked them out. Well, 5 times 5 times 5, or 5 cubed, is 125. Times 4 is 500. So it's like we're unreducing. Okay. All right, this next one looks kind of scary, but don't be intimidated. It's, well, basically the same thing. The only difference is we're not given specific numbers. Okay. So we have xy squared, whatever that is, times the cube root of 4x. Again, whatever that is. We want to write this as one big entire radical. So this 4x is already underneath, so that's fine. We don't have to do a thing with it. But the xy squared, we need to stuff this back in. Well, the same principle applies. Okay? For every xy squared that is outside, we need 3 of them inside. So I'm just going to write 3 of them. So this is the cube root of, give myself lots of room here, okay, of xy squared times xy squared times xy squared. Okay, so 1 of them outside becomes 3 of them inside, and then I still have that 4x here. So all I need to do now is just simplify everything I can by doing some combining. Okay, this is all straight multiplication, so it doesn't matter about the order. So by convention, when we're multiplying a mixture of variables and numbers, we always put the numbers first. Well, the only number present is 4, so I put that first. Let's look at all the x's. I have x to the 1 times x to the 1 times x to the 1 times x to the 1. That's 4 of them. So I can write that as x to the power of 4. Let's look at all the y's. Y squared times y squared times y squared. Remember, when you're multiplying powers, you get to add the exponents. So this becomes y to the power of 6. Okay? So again, same principle. It's not that hard.